We're going to talk about energy methods in this lecture. This will include the virtual work theorem and the potential energy theorem. Virtual work is one of the most general and powerful theorems available. Potential energy is a subcase, and then to tie down our knowledge, we'll have a few problems at the end. We'll start with virtual work, which will be our most powerful theorem for equilibrium statement. There really are three interchangeable statements of equilibrium. You could use Newton's laws, you could use Hamilton's principle, as many physicists do, or you could use virtual work, as we will do. These methods can be applied to both statics and dynamics, but we're not interested in relativity effects nor in thermal problems. That would take more powerful theorems than the theorem that we will use. I found it useful over the years to draw three sketches when I'm discussing a physical problem. I like to show the stress-strain law, the strain displacement, and then the total system behavior in a load deflection curve. So I've shown. Now, these can in fact then be nonlinear as I've shown them. In this course we're going to linearize these figures, but we'll start out with some generality. Let's look at these three figures in more detail. I'll start with the stress-strain law. And in general, it could be nonlinear, where stress would be given as a function of strain, and typically a known function if you know the material. This you could call a nonlinear elasticity, implying that we might move up and down on this curve. There might be, for a given point on the equilibrium curve, point number 1, a corresponding strain and stress. If you wanted to linearize the law about that reference point, you could pass a plane through that point. Now, in fact, that would be a plane in an n-dimensional space, because there might be as many as 6 strains and 6 stresses in a given problem. That would be the case for a solid, for instance. So you might call this a hyperplane. Anyway, down here would be an equation then that would represent that, where you'd have your stress vector as a material matrix G. Then you'd have the strain at the point of interest minus the reference strain. Added on to all of that would be a reference stress. So this is a matter of curve fitting and passing a plane through a reference point. The second figure of interest is the strain displacement law. This is a geometric law and can be hardening, softening, or can even bifurcate. The green strain tensor would be used often to characterize this strain displacement behavior. Now, on the abscissa here, I'm using this Roman U, which is a nodal displacement, and this relation will carry us through to an internal strain epsilon on the abscissa. We'll take our reference point this time on the vertical axis, such that there might be an initial strain epsilon 0, but I'm not accounting for a similar effect on the horizontal axis, because most bodies can be shown in an undeformed state, and so you don't, generally speaking, you don't need an offset in the displacement of the nodes. So we do consider the initial strain, however. The third sketch that I like to show is a system behavior where you have the equilibrium position of the body in terms of system forces and system displacements. So here I show nodal displacement on the horizontal axis, the abscissa, and a force on the vertical axis, the ordinate. And the curve again is a nonlinear system behavior shown in red. And I show this initial position 1, sort of a reference position, and then some general position 2. Now this is the way that I will proceed in following sketches, and 1 is meant to generally be the unloaded, undeformed position in the system sense. And notice that I've put that reference point at the origin. Again, as with displacements, you usually can define a system that's unloaded in terms of live loads. Now, the initial stress and strain quantities that we carried at the material level could be used to account for manufacturing stresses built into the body, or they're used sometimes in nonlinear problems as an artifice to account for some nonlinear behavior and capture it in some linearized form. So we've shown 3 figures of material behavior, geometric behavior, and then system behavior. We've implied that there might be an initial position, Roman numeral 1, that might be a reference position. Then we've implied there might be a more general position 2 out on the load deflection curve. Now we're ready to talk about the virtual displacement. Here I show a body in black as the initially undeformed position. Then I show a red body move slightly to show a loaded and a deformed body. What will be new here is the state 3, Roman numeral 3. And that's going to be considered a virtually displaced position. And the virtual displacement itself is an infinitesimal displacement away from the equilibrium position 2, taking you from that state 2 to a state 3. This must be an admissible displacement. That is, it has to be consistent with the geometric constraints in the problem. If you have a cantilever beam, you may not do a virtual displacement that moves the beam away from the wall, let's say, or gives it a rotation at the wall where it's naturally meant to be a clamped condition. This will cause an increment in all of the displacement-like quantities, such as displacement, strain, rotations, just in general moving the body from the equilibrium position. But the point is that this virtual displacement is a smaller displacement than any of the dimensions of the body, so it really is infinitesimal. Because of that, later we can eliminate some higher order terms that are of order squared in the infinitesimal displacement. It's important for us to have a good definition of work, because I found that many people, in spite of much training in physics, don't really understand what work is. Work is defined in an incremental way, most basically. That is, an increment of work is equal to a force times an increment of displacement. If you keep that in your mind, then you won't fall into a trap that happens occasionally. For instance, some people have said work is force times displacement, and then when some change in the system occurred, they have said that the change in work is the force times the change in displacement plus the change in force times the displacement. Now, on a physical basis, we know that when you hold the position of a body and then change the load, you don't really do active work. There is such a quantity called complementary work, but we normally do not want to discuss that. So beware. I think the way to do it is, and as I've said, is to think of it always in the incremental approach at the top. And if you don't do that, you'll create a fictitious work caused by the force changing. I have seen this once in a situation on a student's dissertation, and it was a case where there was a pressure times an area, and the student varied the area on which the pressure acted. This is actually a part of the load and not a part of the displacement in the direction of the load, and so it added in an extra amount of work. Fortunately, that was small at the time, something like 5%, and then that was changed and improved the answers by 5% afterwards. There is a question in the definition of work as to what is the displacement involved. If a force acts on a body, the question is, what displacement are we speaking of? Is the work a product of force times the displacement of the force, or displacement of the body? And the answer is that it's the displacement of the body that's being acted on. If you're asking the question, how much work does the force do on the body? Now, because of Newton's laws, we know that for every force there's an equal and opposite reaction. And you can get into interesting situations as shown here with this gentleman standing at the base of an escalator. When he squeezes on the moving rail of the escalator, there's a frictional force. That frictional force, in principle, could do work both on the escalator and on the human. Now, in fact, it will do work on the escalator because the escalator is moving, but the frictional force will do no work on the human. So the human, by causing this trouble, has actually caused work to be done, negative work that is, on the escalator. And if you don't think so, you'd ask the motor down in the basement of the building and say, hey motor, have you got some load on you? And the motor would say, boy, do I ever. Somebody's really making me work. Now, of course, if you follow the flow of energy, it goes from the motor to the escalator into the frictional force where it's absorbed, but it isn't given up to the human, so it comes out in heat in this case. This is typical in sliding forces. Work does depend on the coordinate system, and that sometimes surprises people too, because we hear so many invariant laws, such as the conservation of energy, and it doesn't matter in what coordinate system you view that process. But the pieces depend. So, for instance, an easy example would be kinetic energy. If you're riding along with a satellite zipping through the air over the Earth's surface, you feel that the satellite is at rest. But if someone's on the ground and views that satellite zoom by, they say, wow, does that have a lot of kinetic energy? Now let's define virtual work. This is the work done by external and internal forces during a virtual displacement, that is, from state 2 to state 3. It's easier to discuss the work by external forces, particularly if those are concentrated at degrees of freedom I, let's say. Then you take the force at degree of freedom I through the increment of displacement at degree of freedom I, and then sum that over the body with this summation, and that would be the total work done by external forces. If you had gravitational forces, then you would use equivalent nodal loads here. We'll get to that in a bit to find how that will happen, but that's a way of lumping the loads to act at discrete points, so it fits in this mold. Work done by internal forces, unfortunately, is a pretty difficult concept. It takes about an hour or two to develop that idea through variational calculus, and I've found in the past you lose more ground than you gain. You find yourself behind where you were when you started. Let me preview the result of this by saying that it's related to the strain energy. It's actually the negative of the strain energy, and we'll come to that after a bit, and that will be involved in the modified virtual work theorem. I think we're ready now to discuss the virtual work theorem, which is the main thrust of this lecture. And it is that the sum of the internal work done on an elastic body plus the external work on an elastic body during a virtual displacement adds up to 0. Together these are called the virtual work, and that means in an admissible displacement, when you're at equilibrium, there's no work done in total by the external and internal forces. Well, it's pretty easy to demonstrate this theorem for rigid bodies where we just concentrate on the second term here. I like to give the example of the two football players. This might be a Michigan football player and an Ohio State football player that are trying to get in and out of the same hotel door, a revolving door before their game, and they're both all charged up and pushing on that door with perhaps 100 pounds each, as much friction as they can get pushing on the floor. And if those are actually equally balanced, then the rotating door will not pivot at the origin, but will stay there. So then some little baby could come crawling along, some little guy in a nightgown crawls through here, pushes with just a tiny, tiny force on this door. The door will move, and the little baby can crawl on through. Meanwhile, the two players here have swung around to some small distance and are still in equilibrium. If you calculate the work that's done, you find that you have these equal and opposite forces that have been moved through a distance, one of which is a negative distance of the other, and there's no net work done. So I think you can see that, roughly speaking, if the external forces are balanced, then the work they do cancels out when they're just translated or rotated through the same angle, and it's a wash. So you can see that the energy idea and the equilibrium idea are closely related. Rather than use the virtual work theorem directly, I prefer to use what I call the modified virtual work theorem. And this is a subcase where the material is energy conserving, and that would be true for a lot of our elastic problems in vehicle problems in particular, but would leave out the manufacturing problems where there's a lot of plastic flow, for instance in forging and extruding. If this system is elastic in the general sense, it could be nonlinear and elastic, then you can show that the work done by the internal forces is a negative of the strain energy that has occurred in the body. It's really an increment of work equal to an increment of strain energy with a minus sign. That, as I say, though, is a difficult thing to prove. This is the one that's done with a long-winded explanation. I'm just going to state this, though, and not prove it. That's an easy way out. And then you can replace the left-hand side in the original virtual work theorem with this negative strain energy, and so I'll just at this location bring in the new information. Then I have a new equation which I'm going to call a modified virtual work theorem, in which we say net minus the change in strain energy plus the external work equals 0. At first that looks completely unmotivated, but many of you would recognize that if we put the left term onto the right side, you'd see something that looks like a conservation of energy. It really isn't. It's stronger than that. It includes that, but it's stronger than that. You see, it would say that any work done by the external forces would be stored internally as strain energy. And now you see what that assumption of an energy conserving material provides for us, because the energy done by the external forces is not lost, but rather is stored internally. So some of you viewers have had some good physics classes along the way, and I think you're used to conservation laws, and you might say, well, that's just conservation of energy from state 2 to state 3, and we know that. Isn't that always true? No, because conservation of energy usually deals with movement along the equilibrium law from one equilibrium state to another equilibrium state. For instance, going all the way from the unloaded undeformed body to the loaded deformed body. In other words, from state 1 to state 2. But what we're talking about here is more of a vector concept. It says that in any direction of displacement about state 2, no work is done. That means even when you move the body in a direction in which it will eventually not be in equilibrium if you move it that way very far. So you're testing the entire spectrum of the possible motions of the body about its equilibrium position, and you don't get any work done in any of those directions. So it's a much more powerful law than a simple scalar conservation of energy. This is a vector energy law valid for an infinite multitude of trial displacements. I'd like to provide a couple sketches to tie down that feeling about modified virtual work a little more. On the left I have the stress-strain law, and if you move from your state 2 without changing the forces on the system, you would be moving over to this point here, and I don't give that a name right now. Then the area, the green cross-hatched area, would be the so-called strain energy density. If you integrate that over the volume, then you'll get the strain energy. So I show the strain energy density as an integrand here, and then you integrate over the volume to get the total change in strain energy. So that green area has some significance in terms of how much energy is stored in the body. Then at the right we have the work done by the external forces, where we have at state 2 some force system, and then we make a virtual displacement again arbitrarily to the right and get the other green cross-hatched area. The units are proper here, and this does give you an energy equivalence to this area, which would be the work done by the external forces during the virtual displacement. So roughly speaking then, what we're doing is equating these two areas when you properly integrate the area on the left. Its dimensions aren't yet energy, they're energy per volume, but if you integrate this up over the volume, then you get an equivalence between those two green areas. The modified virtual work theorem will be our most powerful tool. Another theoretical tool is the potential energy theorem, and in order to invoke it you have to deal with the most nice and placid of all mechanical systems. They must be linear and energy conserving. To start off, I'm going to do something on the interpretation of the variational operator, and we're going to change our viewpoint. Here we've been talking about an increment of something like displacement, or of work, or of strain energy. And it's possible to think of delta U as if those two symbols are tied together, as if that is a function of x. And you can plot that then, as shown in this figure with the green curve, as a function of x. Now, in a sense, this begs the question of whether the quantity u exists. Mathematically, you could say whether that thing is integrable or not. And the situation is similar to the case of a part-time worker who's working at $5 an hour, perhaps mowing a lawn, and the worker is asked by a friend, what's your annual salary? And the worker says, I don't have any, and I'm working for $5 an hour. But upon persistent questioning, the person ultimately would have to say, look, this is only a small local thing. I'm not guaranteed. I can't necessarily integrate my $5 an hour and tell you that I'm going to make $10,000 a year. It's just not, there's not enough known. And this can happen in the mechanical world also. When we're talking about increments of strain energy or of work done, there are cases where it's not possible to talk about the total work. Those kinds of forces are called circulatory forces. They do not possess a so-called work potential. Now, in this theorem, we're going to pass over, though, to gentle functions that do possess integrals, and that's why we're going to start working with an operator delta now, and we're going to say now that we're going to discuss something delta u in which we really, the delta u implies that you can have a u as a function of x and that you are going to vary it, and you can then show that variation as a function of x as a displacement from the reference function, which I've shown in green, in blue here. So to the average viewer, I know it looks like I'm straining at a point, but particularly in aeronautics, this difference is substantial because wing flutter is a type of a problem that can be studied by the curve above and cannot be studied by the way below because the forces are not integrable. And I'll give an example of that at the as the last homework problem at the end of this lecture. We're going to restrict our attention now to those mechanical systems that have conservative forces and linear elastic material. We'll start out by looking at what it means to have conservative forces. If you have an energy conserving load, that means you can derive the load from a potential field. This is a classical physics idea. In fact, the minus sign that's carried here comes from the physics notation, and I like it. Your potential then, W, would be a function of the variables of the problem. Now for us in finite elements, it would be a function of the nodal displacements. This gradient operator delta here would be a set of derivatives that are stacked up in vector form with respect to those displacement coordinates of interest. So I expand that below to show what is really meant by this then. That del of W would be these partial derivatives on the nodal displacements all the way down to the last one, and then a scalar potential of these variables. So let's try to put our concept of work done by external force over into this new idea that there's a potential function or a work potential lurking there that we can exploit. So we do that by writing the external work done in general. This would be in more physical terms, forces times increments of displacements. This was our fundamental definition of work. Don't worry about the summation sign. This would be summed over degrees of freedom. So this is just sort of a sketch now. We move from the increment idea to the variational idea that now there is a set of displacements that are unique. The delta, we will give the same property as we did the interpretation of a virtual displacement, namely that it only acts on displacement type quantities and it doesn't vary forces. So I'm going to pull that to the outside, and although it acts on the product of force and displacement in principle, due to our definition of this variation as causing virtual displacements, we do not allow it to act on the force part. Now, if you see this, inside you have force at 2 times displacement at 2, and that is rewritable in terms of a field potential here for the loads, and with a minus sign appropriately put in, where we define our work potential to be the minus times the forces times the displacements. So this will be indeed a quantity evaluated at your current equilibrium position. There are different names given for it. You've probably heard me say force potential and work potential already. This is a classical conservative set of loads then. And the common kinds of forces that are conservative are loads that are constant force and direction, gravitational loads, even those gravitational loads in space where they vary as the radius between two bodies and so on. And we will always intend this quantity delta then to vary only the displacement in the problem and not the forces. Now let's look at the simplification of the material in this nice problem. We'll look at a linear elastic system. That will let us write a linear relation between stress and strain, which would be the conventional Hooke's law. If we start out by writing the increment of strain energy as the stress times the increment in strain, and remember that was a green cross-hatched area that we call the strain energy density, and you integrate it over the volume, then we expand the stress into this product of terms because it's going to be a material stiffness times the strain in the body. And that brings us to this form. Then we change our interpretation from an increment of a quantity to a variation of some defined quantity. And that's okay now because we are going to allow that there is a unique strain. Then we'd like to pull the delta out front. To do that, though, we have a paradox because previously we said it could act on displacement-like quantities like strain but not stress. Now we've introduced another strain quantity here rather artificially through the stress law, and so there is a squared quantity here. But by realizing that delta of a quantity squared is the same as 2 times the quantity times delta u, you see that the variational operator uses the same rules as the differential operator or the differentiation itself that follows that polynomial rule. Then we can work backwards and figure that if we're going to let delta operate on strain squared, we've got to put the 1/2 factor to make up for that. Then that really gives us that the change here in total system strain energy is the variation of the strain energy at the state 2. This one is fairly logical, but depends really on the integrability of the strain energy. But for energy conserving bodies, this is guaranteed. This is almost degenerate though, so some of you might say, well, big deal, you know, the professor worked 10 minutes and didn't really tell me anything new. So maybe that's good if you feel that that's very logical. We're ready now to take those 2 simplifications because our system is nice and take the modified virtual work theorem and convert it into a simplified form called potential energy theorem. We will rewrite the modified virtual work theorem here, and then we'll replace the 2 terms as we just discussed. Now the most recent one we discussed that we said was pretty logical is that rather than minus the increment of strain energy going from 2 to 3, you'd rather take the variation of the strain energy at state 2. And then the increment of work done by external forces turned out to be the variation of a work potential with a minus sign that was needed to have the physicist convention. And so if you follow the logic we've had up till now, you really can't stop me from doing this now. It's too late. And I'll factor out the delta out front because the operator now isn't linked to the object that it's operating on as tightly as it was as an increment. So we vary the sum of strain energy plus the work potential. The minus signs have canceled out. And this interesting statement is that the change of this sum total called potential energy right here is 0. And I'll write that down on the next figure. So our very first equation here will be the statement of the potential energy theorem, that the variation of the potential energy of a system at its equilibrium state must be 0. Again, this looks like a scalar law in that you're varying in energy. However, the variation is general and will test the body in all possible admissible motions or displacements. And therefore, this really is a vector concept and will lead to a vector equation of equilibrium when it's used. Another word for the fact that the variation is 0 when you look in all displacement directions is to say that the variation is stationary or that the function is stationary. And that is tantamount to guaranteeing a static equilibrium position. You can extend this method to dynamics and for non-conservative loads by handling the exceptional terms and adding them in, but we won't do that here. The one big use of this theorem is for convergence proofs in linear static analysis. Some textbooks will use the potential energy theorem exclusively rather than virtual work. I think that's fine because there are some nice things that drop out from it. You then are limited to linear elastic systems pretty much, though. So I think I prefer modified virtual work, but it's kind of nice to have both of those theorems available. Well, it's time for a problem session again. And we'll start out by looking at a problem that can be solved purely by energy ideas, and we'll then bring equilibrium in at the end. The question is, can you take a spring such as we have here and drive the force on that spring and the relation with the spring constant purely from energy ideas, not using equilibrium? This is a degenerate enough problem that I've had students that have had great difficulty in doing this because they want to immediately set the force equal to Ku. And that should be the result, not the starting point. What the starting point is, really, is that you have a definition of energy stored in the spring as 1/2 Ku squared. This is presuming the spring is unstretched when it's initially loaded. Therefore, if you increment the displacement by a quantity delta U, you have a new strain energy, 1/2 Ku plus delta U squared. Now, using this information, can you prove that the force here has to be related to the spring stiffness and the displacement in our familiar law F equals Ku, but without using that as an assumption? So don't assume it. You've got to prove it. We'll use the modified virtual work theorem to prove this case. Here we have the modified virtual work theorem. We have to be able to put down the increment of work done by the external force, and that will be the force times delta U through a virtual displacement. The strain energy expression here, delta U, is an increment, so we can literally do that by taking the strain energy at state 3 minus the strain energy at state 2. And that's just the expanded version of strain energy with U plus delta U squared minus the original, this would be an original equilibrium state. And when you multiply this out, you'll get a 1/2 Ku squared term from the first part here that will cancel the original contribution here. So those two cancel. Then we can also cancel the higher order term in delta U squared. So this is a very small virtual displacement, and we'll drop that in comparison with the linear delta U term. So when you get done, you have, interestingly, F delta U equals Ku delta U. Then you factor out the delta U, which is arbitrary, and you ask the question, if that's true, how can that be true for any arbitrary delta U? And the answer is the only way it can be true is if this underbraced term here is 0. And so you therefore have proven the equilibrium law for that system. Now, of course, it's not like magic because we were given at the outset the energy law for the system. But I think it's pretty fundamental, and be sure you understand this simple example, that we didn't put in the equilibrium idea. We got the equilibrium idea out when we knew what the energy relation was. Problem 2 is a twin problem to number 1. Namely, that we're going to again look at a spring, and this time we're going to prove the equilibrium law by starting with the potential energy theorem. Take this linear spring with constant K and a force F on it. It's likely to move through a displacement U from an undeformed, unloaded position. The information we're given is that the energy stored in the spring is a function of the displacement field in the way 1/2 kU squared. And of course, in the back of our mind, we know that the potential energy theorem is valid. This particular load of a constant direction and constant force possesses a potential minus force times displacement. And we can check that if that's not clear to you yet, that we must be able to recover the force through the negative gradient of the work potential. And that means minus d by du of what we are proposing as a candidate work potential here. And when you put in the minus fu and you take a derivative, it will come out with the u canceling, and you get minus f. The minuses cancel and you get plus f from that. So we are prepared now to write out the potential energy theorem. The potential energy itself is the sum of strain energy plus the work potential. We were given the strain energy, and now we have the work potential calculated. And then we must say that the first variation of potential energy is 0 at equilibrium. So we want to form the variation of pi. And we do that with a variation of what we have calculated, the 1/2 kU squared minus fu. The variation acts like a derivative in terms of the cascading of terms. And for the quadratic, you get 2 times ku delta u. 2 cancels 1/2. Over here, you just get minus f delta u. You sum the terms outside the delta u. Since this is arbitrary, and by the way, that is very key, arbitrary, that's why we can say that the term in parentheses here must be 0. And again, we have come up with the equilibrium law for a spring without assuming equilibrium. Even after working out a small problem, many people don't have a feeling for potential energy and the work potential. It is possible, however, in one dimension to draw some sketches of those quantities as functions of displacement. So here on the horizontal axis is the u displacement for our spring problem. And most of you would immediately feel comfortable with the strain energy here in blue being a parabolic quantity with 0 at the origin. With 0 displacement, there's 0 energy, and then you can tell that that's quite rapidly going upwards. The work potential now, the way it's defined, zooms from upper left to lower right, and that's an interesting thing. Many people try to equate the work potential with the amount of work done, and that's not it at all. The work potential, on the other hand, does have a sign convention such that if you think of a ball rolling on a plane for that function, it does tend to throw you in the direction that it would roll down this potential hill. You even hear physicists speak of potential hills and potential wells. That's why I like this sign convention where we carry the minus sign both here and then compensate for it on the recovery of the force, because it gives the proper sign convention for the direction of the forces. When you add the two together, though, of course, that's when you get the potential energy shown in green here. And that is a sum of of course, the blue and the red curves, and they're additive here, naturally, so your green curve for potential energy is higher on the left side. On the right side, the two are subtracting. The minimum is reached here at what we now call the equilibrium position. And don't be confused by this zero crossing. Potential energy is not 0 at equilibrium. Potential energy has a 0 derivative, or it is stationary at equilibrium. So it's this point here. In a linear system with a load at one point like this, you also have a balance that the work potential here happens to be twice what the potential energy is. And the potential energy itself is a negative of the strain energy. So there are some curious relations right here for this simple system, where these things go in thirds, you might say. Problem 3 is a small question about the virtual work being done on a rod. I think it's important to actually get some numerical quantities going here. We're going to take a little rod with 100 newtons acting on it, and here's the rod proper, uniform cross-section, straight, pinned at the left end, load acting at the right end, and the body has come to rest. Now, when there's 100 newtons and you have a stiffness of 100 newtons per millimeter, I think most of you would see that we could find the equilibrium position for sure. So it's sitting out here at some numerical value which we could find across here. We would know the slope here, you see, and we would know this load applied, so we ought to be able to make this transition down here to find the answer. But on top of that, we're told that there's a virtual displacement acting on the body of minus 1/10 of a millimeter. And then we're asking several questions. What is the total virtual work done during that virtual displacement? Think about that. You should figure that out by the time we get to it. How much virtual work is done by the external loads? How much virtual strain energy is created? And so I'm asking about the two pieces that occur in the modified virtual work theorem, and then how much is the total virtual work? Well, the solution to part A of our question is pretty easy. It's exactly answered by the statement of virtual work, because the external work done plus the internal work done equals 0 whenever you do a virtual displacement from the equilibrium position. So the answer is 0. Many times, though, people worry about that even when they've had the virtual work theorem. So I know it's unsettling to get asked something so simple. B says, what is the external work done during a virtual displacement of minus 1/10 of a millimeter? Now that's basically asking what's this shaded green area here, because we've moved from state 1 out to state 2 here under the given 100 Newton load, and then we back up here by 0.1 millimeter in this direction. It's really minus 1/10 millimeter backup. Well, the direct calculation is that the external work done is the force at state 2 times the increment of displacement. So it's 100 newtons times minus 1/10 of a millimeter, and that gives you minus 10 Newton millimeters. Don't be worried by the minus sign, because that can happen. You can have virtual displacements that are negative or positive, because you must test this structure in all directions. Now for part C, we were asked what was the change in strain energy, and rather than try to calculate that for a rod, which you could do, you could also go into it and find stresses and changes in strain, but an easy way is just to use the modified virtual work theorem statement that says that the change in strain energy has to be equal to the work done by the external forces, and that's again minus 10 Newton millimeters. So that's a shortcut. Some of you might be interested to try, though, to go into the interior of the rod, find the stress and the strain, it would be the stress and the virtual strain, and then integrate over the volume and make sure you get the same thing. After introducing the idea of a conservative force and the existence of a potential, I realized I needed to give a good example on this, because I think a lot of people are a little dubious about this business of non-conservative and conservative forces. So problem 4 has to do with potential of forces on a wing. First of all, we're going to look at a single degree of freedom problem here, where there's a wing that's pivoted and can pitch. And the question then would be, just considering the lift force here, acting at the center of lift, which is typically the quarter chord, and typically has these values, does there exist a potential for that situation, for that loading situation? Now the wing can pitch through an angle of attack alpha, And there's a coefficient used in aeronautics, which is a coefficient of proportionality, and says that the load is proportional to that, which carries geometry and some of the airflow general concepts. The Q is the dynamic pressure, 1/2 rho v squared. S is the wing area, and then alpha is angle of attack. The main thing is that lift is proportional to angle of attack. Then secondarily, let's ask if there's a potential for the forces that act on a wing that can both pitch and plunge. Now plunge means it can move up and down in this z coordinate direction. And so now the two coordinates alpha and z enter, and this lift force gives rise to both a vertical force acting on z as well as a moment acting on alpha. And so you have a more complicated problem. So there will be two answers in this problem. One for the left case, it's a single degree of freedom. One for the right case, that's a 2 degree of freedom system. We'll start with the single degree of freedom wing. Here the relevant force is the moment, and that will be some distance epsilon between the center of lift and the pivot point, and then the lift itself. So epsilon is a constant, and then you have the coefficient of lift times q times s times the angle of attack. And the real proof of the pudding here is, does there exist a work potential as a function of alpha such that you can recover the moment as minus the gradient of that work potential? So you have to guess this in a sense. How can we recover the moment up here by taking a derivative? Well, when you see that this is linear in alpha, you realize, gee, if I just doctor up a quadratic potential with alpha squared in it, and then I may have to put the minus 1/2 in here to account for the minus here, and then the variation here, or the derivative. Let's see if this works. You take a derivative then, minus a derivative of that quantity, and the minuses cancel here. When you do the derivative on alpha squared, you're going to get 2 alpha out of it, and the 2's are going to cancel, and lo and behold, you can come up with such a moment. So it's a two-step. It's like you transform into a work potential, and then you transform back to the moment, and that's a two-way street. If you know one, you know the other. That's the classical work potential. Now let's look at the 2 degree of freedom wing and see what happens. This time we have both a moment about the center of interest there, often called the elastic axis in a flutter problem, and then the lift. And so a moment is going to primarily be the generalized force acting on the displacement alpha. Lift is the generalized force acting on the displacement z. And again, the question is, can you find a work potential such that when you take minus the gradient of the work potential, can you recover those two forces? Well, we have an expression for the moment. The moment was related to the epsilon distance times the CL alpha QS alpha, and the question then, if you try to invert this relation rather than a differential relation as we have it, suppose you try to do indefinite integration on these two relations one at a time. So to recover the work potential from the upper equation, you have to do indefinite integration on alpha, which we do here, leading to the alpha squared term, plus a constant of integration, which in fact is an arbitrary function of z, which is the coordinate not being integrated at the moment. Then you look at the second equation and do the same thing, and the question is, can you integrate the lift? Well, the lift is the dCl d alpha times QS alpha, and you integrate it on z this time, and you'll get an alpha z behavior plus an arbitrary function of alpha. So now you really have two conditions that must hold simultaneously, because we've got to be able to map from the right here, from the work potential to the left, and so they must simultaneously hold. So let's see if we can equate these two versions of the work potential. And when we size them up, we have a quadratic term alpha squared on the left with an arbitrary function of z. We have another quadratic but a mixed term alpha z here plus an arbitrary function of alpha. And there's no way you can get that to balance out. You just can't do it. And it's primarily this alpha z term. There's no way to balance it here with a quadratic and with a function of z only. So the answer is those cannot be equated. There is no work potential. The expressions are not integrable. So that will end our problem session.